Okay, there's a lot going on here in this example problem. Basically, using this to go through Lenz's law. That's an important one. The rest of the stuff is review, but Lenz's law is an important concept. All right, and also Faraday's law. So it starts off with Faraday's law. Let's see, what do we have? 20 turns of wire in the shape of a rectangle has a resistance of 5 ohms in the position shown. The loop is in a uniform magnetic field of 0.2 of a Tesla. The B field is directed perpendicular to the plane of the loop and pulled to the right. So very important. This thing, I'm going to redraw the problem so I can work on it. This thing is in a magnetic field. And it's a rectangle of a certain dimension. Let's see if we can make a nice rectangle. Nope, can't make a nice rectangle like that. How about like this? There we go. There's a nice rectangle. Okay, now, this rectangle is going to start off entirely inside here. And we're going to be able to pull it to the right, to here. Now, when it's in the magnetic field, there's a value of 0.2 Teslas. In this region of space, there's a magnetic field of none. So first thing you need to know is that there will be a change in the magnetic flux. Change in magnetic flux, you might remember, is the strength of the magnetic field, or the sort of change in the magnetic field with respect to the area vector. This becomes delta B cosine theta A. Since they're in the same angle, delta B cosine 0 degrees, they're in the same angle. It's the same angle. They're in the same direction. So the angle between them is 0 degrees, A. So cosine of 0 is 1. So this is going to equal delta B times A, because cosine of 0 is 1. Now the area, okay, the dimensions of this rectangle were dimensions of the rectangle, 0.15 meters over here and 0.25 meters over there. So that shouldn't be too hard. 25 times 15, or we should say 0.25 times 0.15. The area is 0.0375 square meters. Delta B is going to change from 0.2 to 0. Anytime you see delta, remember, you have to go final minus initial. So this is really going to be 0 minus 0.2 Teslas. So the delta phi here, anytime you see delta, in this case it's delta phi, is going to be, I shouldn't say delta phi, I should say delta B. Delta B, just the magnetic field. The delta B in this case will be 0, negative 0.2 of a Tesla. From 0 to negative minus 2, 0 minus 0.2 is negative 0.2. So we can figure out the change in the magnetic flux, delta phi. Delta B, negative 0.2 Teslas. And the area, 0.0375 meters squared. negative 0.0075 Tesla meters squared, or 0.0075 Webers. That's the change in flux. They really don't want us to know about the delta flux. The first thing we have to know is EMF. Here's where Faraday's law comes in. Faraday's law says EMF, or epsilon, is equal to negative n, the change in flux with respect to time. Oh, all right, so what do we say? What's n? N, we say, is 20 turns. N equals 20. N stands for the number of loops. And our time is a half a second. It goes from inside this region to outside this region in a half a second. So now just plug and chug. Negative 20 turns times negative 0.0075 Tesla meters squared with respect to time, which was a half a second, 0.5 seconds. Do this math. That times 20 divided by 0.5, we end up with an EMF of 0.3 volts. That's one. This is Faraday's law. Very important to know Faraday's law. It's right here. Faraday's law. Know it. What else do they want to know? Calculate the magnitude of the current in the coil and state its direction. This is not too hard. The magnitude of the current. We're very familiar. You should remember Ohm's law. V equals IR. We don't have voltage here. It's not connected to a battery, but it is. There is a voltage of 0.3 volts. So Ohm's law, you might as well write electromotive force equals current times resistance. We were told the resistance of the wire loop was 5 ohms. And now we just calculated this. So we get 0.3 volts is equal to some current times 5 ohms. And now divide 0.3 by 5, and we get the current to be 0.06 amps. Now, here's the tricky part. We not only have to state the magnitude of the current, but we need to know its direction. So as this rectangular loop of wire goes from here to here, current can either be flowing, current could be flowing in the clockwise pattern, maybe, or current could be flowing in the counterclockwise. We got to figure out which way. This is where you need Lenz's law to figure this out. To figure out what's going on, you need to use Lenz's law. And that Lenz's law is why there is a negative here, to figure out the direction. Lenz's law. What direction is this current in? So right now, this thing has magnetic flux out of the screen. It wants to keep magnetic flux out of the screen. That's what those dots mean. It means the magnetic field is out of the screen. It wants to keep it that way. Lenz's law says that this thing will resist changes in magnetic flux. So if there were, 6 dots in there, and we pull it to the right, and now there's only 4 dots in there. There's less magnetic flux out of the screen. It doesn't want to have less. It wants to have more. It wants to maintain its 6. It doesn't want to have 4. It doesn't want to have 2. It doesn't want to have 0. It's going to induce a current that's going to keep magnetic flux. It's going to force magnetic flux out of the page. So current will flow in the direction to put a B field out of the page. We're going to use our right-hand rule solenoid, or right-hand rule number 3. Right-hand rule number 3 backwards. Okay? Now, the thumb is going to represent the magnetic field lines. So get your thumb going out of the screen of your right hand. If the thumb of your right hand is going out of the screen, your fingers are curling. If the thumb is going out of the screen of your right hand, make sure you're using the right hand, your fingers should be curling this way. So as this thing goes, the current's going to be flowing like so, and that general direction is counterclockwise. So you'll have a current of 0.06 amps in the counterclockwise direction. Thank you, Lenz Law. Now they also want you to, they have a few more problems for you to go through. Power. Power is easy. Power, do it over here. This is part 3. Power equals VI. We know the voltage, 0.3 volts. We now know the current, 0.06 amps. So the power is 0.06 times 0.3, 0.3 times 0.06, 0.018 watts. That's easy. 0.018. Why isn't that snapping into a shape? I don't know why. Yeah. Okay. Calculate the magnitude of the average force. This one's tough. This is an interesting question. To figure that out, I'm going to erase some of this picture here. Get rid of that. Okay, now, if you would, let's go back to where we started. We have some magnetic field lines here and here. The magnetic field is out of the page. And we have our coil of wire. Not grabbing for some reason. Our coil of wire here. When we pull it to the side, current is going to be induced. The current that is induced, we know the current that is induced is going this way, this way, this way, and this way. When current flows, that will generate a magnetic field. So this current is going to produce some magnetic field that is going to be round, circular, and perpendicular to the wire. This wire here is going to produce current that is round and perpendicular to the wire. This wire here, as current flows through it, is going to produce circular, concentric magnetic fields perpendicular to the wire. And this one over here is going to produce like so. However, any part of the wire that's not in a magnetic field There's no other existing magnetic field for this magnetic field to interact with, to push or pull. So everything that is out of the magnetic field, we can ignore. There's no other magnetic field for those two magnetic fields to interact with. There's not going to be a push or pull. It's like holding a magnet in the air. It's not attracted or pulled to anything. It's got to come in contact near another magnet. So here, there is this magnetic field over here, but it's not going to produce any force on anything because this no other magnetic field is going to repel or push it. So we can ignore this. Now these two fields are going to interact, and we can use our right-hand rule number 2, or right-hand rule flat. Right? Current is going one way, so across the current, there's going to be a magnetic. Let's say we have a positive charge. If the current is the flow of positive charge, conventional current, we've got positive charges moving this way. Over here, we're going to have positive charges moving that way. Get the fingers of your right hand pointing out of the screen. The fingers of your right hand pointing out of the screen. Thumb above the wire is this way. This is going to generate a force. This is going to generate a force upward this way, based off of right-hand rule number 2. Down here, fingers out of the screen, thumb to the side. This is going to generate a force down here. These two forces will be equal and opposite, and they will cancel out. Doesn't matter. However, these two magnetic fields are going to produce a force. Once again, we will have conventional current. We will have a positive charge moving in that direction. Use right-hand rule number 2. Thumb down the screen, fingers out of the screen. That is going to produce a force. That will produce a force this way. The magnetic force will be that way. Magnetic force will be that way. And that should make sense. Calculate this force we want to calculate on this wire, but the direction of that force is going to be to the left. The direction of the force is going to be to the left. And the magnitude of that force, the magnitude of the force that is to the left on that wire, we calculate magnetic field intensity times the current times the length of the wire. And I really should say this. I think your reference tables write it slightly differently. Your reference tables, your equation sheet writes it IL cross B. Because the current and the magnetic field are at right angles to each other, you can say IL sine theta B. They're at right angles. That's going to be IL sine 90 degrees B. 90 degrees being 1. So basically ILB. The current we figured out, 0.06 amps. The length, again, whatever force we get here and whatever force we get there, they're going to cancel each other out. So we're going to ignore that. And we're only going to use this one. And so only this length of wire, which was 0.15 meters, and the B was 0.2 of a Tesla. So the magnetic force will be 0.06 times 0.15 times 0.2. The magnetic force equals 0.0018 newtons. But this is really, really tricky. They're going to screw you up. You can't forget the fact that there are 20 loops of these wires. There are 20 loops of these wires. Holy cow. So each time, 1, 2, 3, 4, 5, 6, each one has this force times 20 coils. So we get the force, the net force, to be 0.036 newtons. Calculate the magnitude of the average force necessary. So there, we've got that one. Don't forget that it's a 20 coil. You got to multiply the force by 20. Last part, holy cow, identical wire is used to add 20 more turns. What if they added 20 more loops to the original coil? How does this affect the current? What if in the very, very start, they added 20 more loops? How would that affect things? If they added 20 more loops, if this wasn't 20, if this was 40, what would happen then? Well, how would that affect the current? Well, with 20 more loops, if we double the number of loops, we would double the voltage. The new EMF would now be 0.6 volts. And it's the same thing. We would get 0.6 here. Okay, how does that affect the current in this wire? We would get double the voltage. Ooh, if we double the number of loops, we're doubling the length of wire. We're also going to double the resistance, aren't we? Yes, we would double the resistance. So what would happen? The answer is we'd get 0.6 volts equals some current times 10 ohms, and you get the current of 0.06 amps. You get the same current. Because if you change the number of loops, you're also going to end up changing the resistance at the same rate. So you get double the voltage, double the resistance, the same current. That's a long problem. That takes, I don't know, that should take you 20 minutes or so on an AP exam to get through that problem. That's it.